In Part 3 of Lecture 3, we will discuss suspended processes. Recall that the reason for all of this elaborate machinery is that input-output activities are much slower than computation, and therefore the processor in a uniprogramming system is idle most of the time. But the arrangement that we saw in the earlier figure does not entirely solve the problem. It is true that in this case, memory holds multiple processes and that the processor can move to another process when one process is blocked. But the processor is so much faster than input-output that it will be common for all of the processes in memory to be waiting for input-output. Thus, even with multiprogramming, a processor could be idle most of the time. What to do? Main memory could be expanded to accommodate more processors, but there are two flaws in this approach. First, there is the cost associated with main memory, which, though small on a per byte basis, begins to add up as we get into the gigabytes of storage. Second, the appetite for programs for memory has grown as fast as the cost of memory has dropped. So larger memory results in larger processes, not more processes. Another solution is swapping, which involves moving part or all of a process from main memory to disk. When none of the processes in main memory is in the ready state, the operating system swaps one of the blocked processes out onto disk in a suspend queue. This is a queue of existing processes which have been temporarily kicked out of main memory or suspended. The operating system then brings in another process from the suspend queue, or it honors a new process request. Execution then continues with the newly arrived process. Swapping, however, is an input-output operation, and therefore there is the potential for making the problem worse, not better. But because disk input-output is generally the fastest input-output on a system, for example, compared with tape or printer input-output, swapping will usually enhance performance. With the use of swapping as just described, one other state must be added to a process behavior model, the suspend state. When all of the processes in main memory are in the blocked state, the operating system can suspend one process by putting it in the suspend state and transferring it to disk. The space that is freed in main memory can then be used to bring in another process. When the operating system has performed a swapping out operation, it has two choices for selecting a process to bring into main memory. It can admit a newly created process, or it can bring in a previously suspended process. It would appear that the preference should be to bring in a previously suspended process, to provide it with service rather than to increasing the total load on the system. But this line of reasoning presents a difficulty. All of the processes that have been suspended were in the block state at the time of suspension. It would clearly not do any good to bring a blocked process back into main memory because it is still not ready for execution. Recognize, however, that each process in the suspend state was originally blocked on a particular event. When that event occurs, the process is not blocked and potentially available for execution. Therefore, we need to rethink this aspect of the design. There are two independent concepts here: whether a process is waiting on an event blocked or not, and whether a process has been swapped out of main memory, suspended or not. To accommodate this 2x2 combination, we need 4 states. Ready. The process is in main memory and available for execution. Blocked. The process is in main memory and awaiting an event. Blocked suspend. The process is in secondary memory and awaiting an event. Ready suspend. The process is in secondary memory but is available for execution as soon as it is loaded into main memory. Before looking at a state transition diagram that encompasses the two new suspend states, one other point should be mentioned. The discussion so far has assumed that virtual memory is not in use and that a process is either all in main memory or all out of main memory. With a virtual memory scheme, it is possible to execute a process that is only partially in main memory. If reference is made to a process address that is not in main memory, then the appropriate portion of the process can be brought in. The use of virtual memory would appear to eliminate the need for explicit swapping, because any desired address in any desired process can be moved in or out of main memory by the memory management hardware of the processor. However, as we shall see in Lecture 8, the performance of a virtual memory system can collapse if there is a sufficiently large number of active processes, all of which are partially in main memory. Therefore, even in a virtual memory system, the operating system will need to swap out processes explicitly and completely from time to time in the interests of performance. Let's take a look now at the state transition model that we have developed. The dashed lines in the figure indicate possible but not necessary transitions. Important new transitions are the following: blocked to blocked suspend. If there are no ready transitions, then at least one blocked process is swapped out to make room for another process that is not blocked. This transition can be made even if there are ready processes available, if the operating system determines that the currently running process or a ready process that it would like to dispatch requires more main memory to maintain adequate performance. Blocked suspend to ready suspend. A process in the blocked suspend state is moved to ready suspend state when the event for which it has been waiting occurs. Note that this requires that the state information concerning suspended processes must be accessible to the operating system. Ready suspend to ready. When there are no ready processes in main memory, the operating system will need to bring one in to continue execution. In addition, it might be the case that a process in the ready suspend state has a higher priority than that of the processes in the ready state. In that case, the operating system designer may dictate that it is more important to get at the higher priority process than to minimize swapping. Ready to ready suspend. Normally, the operating system would prefer to suspend a blocked process than a ready one, because the ready process can now be executed, whereas the blocked process is taking up main memory space and cannot be executed. However, it may be necessary to suspend a ready process if that is the only way to free up a sufficiently large block of main memory. Also, the operating system may choose to suspend a lower priority ready process rather than a higher priority blocked process if it believes that the blocked process will be ready soon. Several other transitions that are worth considering are the following: new to ready suspend and new to ready. When a new process is created, it can either be added to the ready queue or the ready suspend queue. In either case, the operating system must create a process control block and allocate an address space for the process. It might be preferable for the operating system to perform these housekeeping duties at an early time, so that it can maintain a large pool of processes that are not blocked. With this strategy, there would often be insufficient room in main memory for a new process, hence the use of the new suspend to ready suspend transition. On the other hand, we could argue that a just-in-time philosophy of creating processes as late as possible reduces operating system overhead and allows the operating system to perform the process creation duties at a time when the system is clogged with blocked processes anyway. Blocked suspend to blocked. Inclusion of this transition may seem to be poor design. After all, if a process is not ready to execute and is not already in main memory, what is the point of bringing it in? But consider the following scenario. A process terminates, freeing up some main memory. There is a process in the blocked suspend queue with a higher priority than any of the processes in the ready suspend queue, and the operating system has reason to believe that the blocking event for that process will occur soon. Under these circumstances, it would seem reasonable to bring a blocked process into main memory in preference to a ready process. Running to ready suspend. Normally, a running process is moved to the ready state when its time allocation expires. If, however, the operating system is preempting the process because a higher priority process on the blocked suspend queue has just become unblocked, the operating system could move the running process directly to the ready suspend queue and free some main memory. Any state to exit. Typically, a process terminates while it is running, either because it has completed or because of some fatal fault condition. However, in some operating systems, a process may be terminated by the process that created it, or when the parent process itself terminated. If this is allowed, then a process in any state can be moved to the exit state. We can generalize the concept of a suspended process. Let's define a suspended process as having the following characteristics. The process is not immediately available for execution. The process may or may not be waiting on an event. If it is, this blocked condition is independent of the suspend condition. An occurrence of the blocking event does not enable the process to be executed immediately. The process was placed in a suspended state by an agent, either itself, a parent process, or the operating system, for the purpose of preventing its execution. The process may not be removed from this state until the agent explicitly orders the removal. The table on this slide lists some reasons for the suspension of a process. One reason that we have discussed is to provide memory space either to bring in a ready suspended process or to increase the memory allocated to other ready processes. The operating system may have other motivations for suspending a process. For example, an auditing or tracing process may be employed to monitor activity on the system. The process may be used to record the level of utilization of various resources, processor, memory, channels, and the rate of progress of the user processes in the system. The operating system, under operator control, may turn this process on and off from time to time. If the operating system detects or suspects a problem, it may suspend a process. One example of this is deadlock, which will be discussed in Lecture 6. As another example, a problem is detected on a telecommunications line, and the operator has the operating system suspend the process that is using the line while some tests are run. Another set of reasons concerns the actions of an interactive user. For example, if a user suspects a bug in the program, he or she may debug the program by suspending its execution, examining and modifying the program or data, and resuming execution. Or there may be a background process that is collecting trace or accounting statistics, which the user may wish to be able to turn on or off. Timing considerations may also lead to a swapping decision. For example, if a process is to be activated and periodically and is idle most of the time, then it should be swapped out between uses. A program that monitors utilization or user activity is an example. Finally, a parent process may wish to suspend a descendant process. For example, process A may spawn process B to perform a file read. Subsequently, process B encounters an error in the file read procedure and reports this to process A. Process A suspends process B to investigate the cause. In all of these cases, the activation of a suspended process is requested by the agent that initially requested the suspension.